Hello. Today I'm going to be talking about federated learning for prostate cancer detection on MRI. So this is a work which we at Emory University are doing in collaboration with Rhino Health. Briefly about myself, my name is Rakesh Shiradkar. I'm an assistant professor of biomedical engineering at Emory University and Georgia Tech. And Pranav Sompalle is a student intern at biomedical engineering, Case Western Reserve University, who is working with me on this project. Prostate cancer affects a significant percentage of men worldwide, and increasingly multiparametric MRI is being used for prostate cancer diagnosis. Prostate MRI typically consists of T2-weighted, diffusion-weighted, and ADC sequences. Recently, there has been a significant usage of development of AI tools for prostate cancer detection on MRI. And here, as you can see, this is the result from a deep learning model for prostate cancer detection on MRI. However, the AI tools are still not ready for clinical translation due to significant challenges for reliable AI. One of the main challenges is the variability in MRI scans across various sites. As you can see in this image, there is significant variation in the quality and resolution of MRI. And the other challenge is the ground truth definition that is used for training the AI models. It could either be from biopsy or surgical specimen or radiologist reads. One of the solutions for tackling these challenges is to leverage multi-site, multi-scanner data to improve the heterogeneity of the data sets and therefore improve the reliability of AI models for prostate cancer detection. However, leveraging multi-site data has its own set of challenges, including regulatory bottlenecks, patient privacy, costs associated with storage and data transfer. So there's a need for decentralized and privacy-preserving networks. Federated learning is a recently developed technology which allows for decentralized and privacy-preserving training of AI. And Rhino Federated Computing Platform is a very convenient solution for deploying federated learning. And I will now let Pranav Sompalle, the intern student, take over and talk a little more about the project for federated learning of prostate cancer detection. Pranav, take it from here.
In our study, we used the Prostate Imaging Cancer AI, or PICAI dataset, which consists of 1,499 patients. And we only selected 213 of those patients because they had clinically significant prostate cancer determined by the International Society for Urologic Pathology grade group and available annotations for both their prostate cancer and their prostate gland. The modalities that were available for each patient consisted of prostate biparametric MRI, which consists of intensity standardized T2-weighted or T2W images, and registered apparent diffusion coefficient or ADC maps, as well as AI-generated prostate whole gland mass and human annotated ground truth cancer mass. To simulate federated learning in our project, we conducted 3 random samples without replacement on the 213 patient cell population we selected from the PICAI dataset. Our deep learning model was a UNet designed for specifically tumor segmentation on prostate biparametric MRI sequences, and a sample architecture of a UNet can be seen on the right in this image. Our project began with the development of our UNet model for prostate tumor segmentation. After developing and error-proofing this UNet model, we containerized and NVIDIA Flare adapted the model so that it could be integrated into the Rhino FCP. Each patient's MRI portfolio from the PICAI dataset was assigned into a randomly determined site, which was then imported as separate cohorts into the Rhino FCP, specifically sites 1 through 3. In the Rhino FCP, we began with a traditional learning or TL experiment. In the TL experiment, we set the site 1 for training and testing and site 3 for external validation, in which the model would use weights, the best metric weights determined in site 1's training and testing to conduct external validation on site 3. We also completed a federated learning experiment in which we would use 2 sites for simultaneous training and testing using 2 separate FL clients. We would then complete external validation on site 3's 71 patients after aggregating the separate weights, the separate best metric weights determined in site 1 and site 2's training and testing through an aggregator, which would then export weights into the model for its external validation on site 3. In our traditional learning experiment, we could observe a typical decline in dice loss, as well as a moderate increase in dice metric, as well as typical distributions of dice coefficient and Jacquard indices. On the other hand, in the federated learning experiment, we could observe similar trends in dice loss and dice metric over training and testing, as well as we could determine a moderate increase or minor increase in dice coefficient, as well as Jacquard indices relative to the traditional learning experiment. However, more work is required. This is just a comparison of some slices generated for a few patients in the federated learning and the traditional learning experiments, in which we can observe a minor improvement in coverage by the prediction mask, the prediction tumor mask, compared to a ground truth mask, relative to a traditional learning experiment.
Thank you, Pranav. It's definitely a work in progress, and we hope to demonstrate feasibility with simulated multi-site data through this experiment. Going forward, our next step would be to train and validate on real-world multi-site data, and we're always looking for collaborators with access to prostate MRI data to further improve and refine our AI model for prostate cancer detection. Here is our contact, and this is our lab directed by Dr. Anand Maribushi. Thank you.